Alright, I'm going to be talking about diffraction today, and diffraction deals mostly with the wave property of light. So light has two properties. It can be thought of as a particle, as a solid unit, or it can also be thought of as a wave, having a wave function. So I'm going to erase this real quick. So first type of diffraction that we're going to talk about is with a single slit. So what happens is that the light comes in as a wave, and there's usually a very bright peak in the middle here, followed by a dark band, light band, and a dark band. So what happens in the dark bands is you have some waves that come out here, and then waves that meet up, and they have destructive diffraction, where they destroy each other, and that's why you get a dark spot. Where in other areas you can have a light wave coming here, and then another light wave, and you have constructive diffraction, where they add up and you get a bright spot. This is kind of like in the middle. Now, one useful equation for a single slit is d sine theta dark is equal to lambda divided by m, where m is equal to plus or minus 1, plus or minus 2, etc. And this will tell you where the fringes of the dark regions are for a single slit. Now we're going to talk a little bit about a dual slit. So what happens is the light comes in here, and then again you have some constructive diffraction where the light builds up and you get an intense peak here, and then there'll be a dark region here followed by more constructive diffraction, and you'll have another bright spot here. And then you'll have another one here and here, followed by these regions that are dark. Now I'm going to talk a little bit about X-ray diffraction. So, X-ray diffraction. So usually what they do is they use some X-ray source. So let's say this here, designated by X, and they'll have some type of crystal. Let's say just whatever crystal that this is. And they'll shine X-rays at it, and then these get bounced off onto a screen that creates a very distinct pattern for each crystal. And based on this pattern, we can determine the structure of the crystal. Now I'm going to do a really quick problem. So I have a light of lambda equal to 632.8 nanometers, and then the distance of the slit is equal to 0.3 millimeters, and then the L, the length from the screen, is equal to 1 meter. So drawing this real quick, this is L, distance from the screen. Then this distance here is 0.3 meters. Now I have light coming in, like so, which has this wavelength. So what the question is asking is to find the distance of the bright, strong peak here. So what we're going to do is we're going to use the equation from earlier, which is d sine theta dark is equal to, or we're going to use equation sine theta dark is equal to m lambda divided by a, or distance, where m is equal to plus or minus 1, plus or minus 2, etc., etc. And we're only concerned with m equals 1 because we want the distance to this dark fringe and to this dark fringe. So we want the absolute value of this. So first we're going to say that tangent of theta dark is equal to y divided by L. and this comes from this. We're halfway at the middle peak, and then out here somewhere, and we're going to say that this component here is y. And then we're going to say that tan theta dark is roughly equal to sine theta dark. So ultimately, once we plug this in here, we're going to get that the length times sine theta dark is equal to y1. Now, we want the distance from here to here, so we're going to take the absolute value and multiply that by 2, which is the same thing as adding this component and this component. So I rearrange this, and I get that 2 absolute value y1 is equal to L sine theta dark absolute value, which is also equal to 2L lambda divided by D. And then plugging these values into here, and I get that the distance from here to here is 4.2 millimeters.